welcome to the Maths and Science Corner. And today, without wasting any time, we're going to be looking at question 5 of paper 1 Physical Sciences, which is work, energy, and power, right? So, I would advise you to first try to attempt the question and then look at the solutions as we do them, right? So, we're gonna just read the question and see what we are dealing with, right? So they're saying that water is drawn from a water source 12.5 meters below the ground by an electric pump, right? So the water is lifted vertically upwards at a constant speed as shown in the simplified diagram below, right? So what information can we get from that? We know that, okay, our height is 12.5 meters. There we have it. This is our height below the ground. And we also given that this water moves at a constant velocity, right? What does this mean? It means that our V final is equal to our V initial, right? Which also means that our F net, the net force acting on that amount of water as it goes up, is equal to 0, right? So now they say the pump lifts the water upwards at a rate of 2.5 kilograms per second, right? Ignore all frictional and capillarity effects. So what is this? What is this thing that we're given here? We're given the rate, right? So the rate, what the rate tell us is how fast or how slow something is getting used up or is occurring, right? How fast something is occurring, right? So this is telling us the rate at which the water is being lifted upwards, right? So this means that 2.5 kilograms, right, is lifted every second, right? Because they said per second. So each and every second, we have 2.5 kilogram of water being lifted from the water source to the ground each and every second, right? So that is our rate at which the water is being lifted upwards, right? So now we're going to look at 5.1, right? So 5.1, what do they want? They want us to define the term non-conservative force, right? So we're going to define it in a way that it is stated in the exam guideline, right? So it is a force for which the work done on a moving object, right, between 2 points is depends, or let me just say depends, or you could say it's dependent, right? So it depends on the path taken, right? So that is our definition of a non-conservative force, right? So that is our 5.1. So we're going to look at 5.2 now. So for 5.2, what are they saying? They say draw a labeled free body diagram showing all the forces acting on a fixed, right, on a fixed mass of water as it moves from the source to the ground. So we know that the water is moving from the water source to the ground, right? So they're saying that, just imagine if you had a fixed amount. Let's say, for example, the fixed amount was 10 kg or anything, right? So they're saying that fixed amount, as it moves from the water source to the ground, what are the forces that are acting on that amount of water, right? So there we have our mass. Then we're going to look at the forces that are acting. We know that as long as we are still near the ground, the surface of the earth, there's always going to be a force that acts downwards, right? So that is our force of gravity, right? And if we have our force of gravity, we know that we also have another force which is pulling this water from the water source to the ground, right? Because it can't just go up if there's no force that's lifting it up, right? So we know that we are given that that force is the force of the pump, right? So we have the force of the pump and the force of gravity, right? Or you could have just said, this is the same thing as the weight, right? It's the same thing as the weight, right? And this is your force of the pump, right? So, um, and so I think these are the only forces that are acting on that amount of water, right? So from there, we can go to 5.3, right? Okay, so now we're gonna be looking at question 5.3, right? So we have 5.3. So they're saying now calculate what the work done by the pump, right? So in order to find the work done, we know that our work net is equal to, obviously, using the work energy theorem, we know that, okay, we don't have to use the work energy theorem. We know that our F net times our delta X times our what? Our cos theta, right? This is our work net formula, right? So if we do this, then we know that this work net is a what? Is a combination of the work done by the pump and the work done by the force of gravity, right? So this is the work done by pump plus work done by gravity, right? Is equal to our F net, which is just 0 times, no matter what our height or our cos theta is, it doesn't change the fact that all of this will still be 0, right? Regardless of whatever we have here. But we know still our delta x is h, and we know that our cos theta will just be cos 0, right? But then regardless, this will still be 0. So we know that our work done by the pump plus the work done by gravity is equal to 0, right? So therefore, our work done by the pump is equal to negative the work done by gravity, right? So when we have this, we can say what? We can say that we know that our force of gravity is what? We know that, okay, this is what the work done by the pump is equal to. The work done by the gravity, right? By gravity will obviously be negative, right? This negative multiplied by, so we know that there's this formula that we know that the work done, let me just write it here, the work done by gravity, right? Since gravity is a non-conservative force, it's a conservative force, I mean gravity is a conservative force, and the work done by gravity is always calculated as negative change in potential energy, right? This is the formula that we use to calculate the work done by gravity. So, this is equal to negative, right? But okay, this is negative what? Mg H final minus H initial, right? So we're gonna use this formula and just plug it in here, right? So this is negative. Our M is what? We know that is 200. Our G 9.8, right? So then our difference in height, since we said, okay, let's take our direction, let's say up is positive, right? So if up is positive, then we have what? Our final height will be, so our initial height is 0, and our h final is equal to 12.5, right? So that means we are up 12.5 meters, that is positive 12.5, right? So this is 12.5 minus 0, right? So after that, we now have our work done by the pump, which is negative. Let's try to type that into the calculator and see. So let me just type this. So this is 200 times 9.8 times 12.5, right? So this is 24,000. Actually, it's positive. So it's positive 24,500, right? Joules, right? So this is the work done by the pump. So if you look at, now we're going to look at, so this was our 5.3.1, right? So now we're going to look at 5.3.2. So now they're saying what they're saying, calculate the constant speed at which the water is lifted, right? So since we want the speed, we said that the water is being lifted at a constant speed, right? So now they're saying we should find that speed which it is being lifted at, right? So if we look at something here, we know that, okay, our formula for speed will have for constant speed, right? For constant speed, we have speed is equal to our change in x, right, divided by our change in t, right? So this is our formula for constant speed only, right? We write this down, constant speed only. So if it's not constant speed, that means we need to use maybe the equations of motion or other alternative methods, right? But then for constant speed, this is our formula, right? So, but if you look at this, we don't have the time, right? We don't have the time. We don't know how long does it take for 200 kg to reach the ground, right? To move from the water source to the ground. We don't know how long it takes. But we know something, right? We know that 2.5 kilograms per second is lifted every second, right? So 2.5 kilograms is lifted every second. So with that, we have that ratio, right? We can just say 2.5 kg is lifted, right? Every second, which means 1 second, right? So we can just write this ratio. You know, this is a ratio, right? So it's 2.5 kg per second. So what we can do is that we can say now, okay, instead of 2.5 kg, what do I have? I have 200 kg, right? So if I have 200 kg, how long will it take? I can just let that, okay, let me not use x because it's going to confuse with this x. Let's just use b, right? Let's just say b is our time, right? So, but let me just use t because, yeah, I think it makes more sense with t. So, it takes 1 second for 2.5 kilograms. How long will it take? 200 kilograms, right? So now we can just cross multiply. We have 2.5 kg, right, times t is equal to 1 second. 1 second times what? 200 kg. So now what we can say is that, okay, we can just try to solve for t. We have t is equal to 1 second, right, times, actually you don't have to carry these units, but I just want so that so we can see when things cancel out, right? So it makes more sense so that way. So we have 200 kg divided by what? Divided by 2.5 kg, right? So from that we can see that, okay, kg and kg, they cancel. So 1 is just 1, so we just left with seconds, right? So basically our t is equal to 200, right, divided by 2.5, and that is equal to, let me type that, that's 200 times and divided by, 2.5. So this is 80 seconds, right? So this is 80 seconds. So if you have this 80 seconds now, that means you have your what? Your delta t, right? So you have your delta t now. So if you have your delta t in okay, you can now find what? The velocity. So now your velocity is what? V is equal to your change in x. We know that obviously it's moving from where? It's moving from the water source to the ground, right? So it's 12.5 meters. So we have our 12.5 meters divided by our time, which is 80 seconds, right? So that will give us our velocity. So this is 12.5 divided by 80 seconds. So this is 0.1565 seconds, right? Which is approximately 0.16. Oh, sorry, this is not seconds, it's meters per seconds, right? Meters per second. Meters per second, right? So this is our velocity, right? So now they're saying what? Calculate the average power dissipated by the pump. Ignore any energy losses in the form of heat or sound, right? So we know that no energy is lost and no heat creates any energy losses, right? So if you look at 5.3.3, we can see what actually we have two formulas to calculate power, right? So there are two formulas. The first formula is to say that power is equal to the work done divided by change in time, right? This is our first formula. Or we can use which formula? We can say power average, which is the average power, is equal to the force, right? The force times the velocity average, right? So these are the two formulas that we can use to calculate power, right? These are the two formulas available. So okay, let's see if we can use one of them to calculate the power, right? Okay, so we're gonna say power is equal to the thing, the power of what? The power dissipated by the pump, right? This is important, by the pump. So we are only focusing on what? The pump, the force of the pump, or the work done by the pump. So we know that the work done is 24,500, right? So this is 24,500, right? Divided by the time it takes. So how long does it take? It takes 80 seconds, right? We have already discovered that it takes only 80 seconds. So if you calculate that, we should get, let me put that, 24,500 divided by 80. So this is 306.25 watts, right? So this is what we have as our power. So this is our power. So let's use a different formula and see if we get the same thing. But then this would be you are done at this point, right? But then just for interest sake, let's just try to see if this formula also works, right? The average power will be the force. This one will need us to calculate the force, right? But since we know that, okay, the force of gravity going down here and the force of the pump, they are equal because this thing is moving at a constant velocity, right? So these two forces are equal. So I can say that as my force, I can say this is equal to what? 200 kg times my what? My 9.8, right? This is my force. And my V average is what? 206 point, oh sorry, this is not my V average. My V average is what? Let me just write it the whole part, right? Or let me just write this 12.5 over 80. You know, this is 12.5 over 80, right? So if we type that into our calculators, So this is 200 times 9.8 times 12.5, right? All of that divided by 80, which is the same thing, 306.25 watts, right?